the little board with the LED light. You remember we all did this, right? Okay. So some of you were asking like why are we using this resistor, or like, yeah, how did you know to size it up that way? So in order for us to know that, we had to go into some basics of electricity, and this is also going to become useful later when you are trying to understand battery sizing too. Okay, because I mean, there's different. If you look at a battery, I have a couple. Let me just pass them around. If you look at a battery, you're going to notice there is a bunch of different numbers and stuff on them. Careful with this one. This one's like the leads are all broken. But yeah, so in order for us to understand what's going on, you need to. Oh, you got your own batteries. In order to understand what's going on, we have to understand some electricity. Okay. So this will be useful beyond just soldering our own little projects down here. Okay. All right. So, okay. Have you guys heard of any of these terms? Yeah. Does anyone know what these mean? Anyone care to, or give it a shot if you don't know what it means? Yes.
Voltage is the amount of power that you're going to see in like your OCH, your on-screen display.
Yeah.
For the current is how much of that it's drawing, right?
Yeah.
Power is what's stored inside of the battery to provide voltage and current, or is that energy?
Energy is going to be time-based.
Okay.
So what you use, and then what SCE charges you, they charge you for how much power you used over a period of time.
Okay.
Yeah, that's basically energy. Yeah.
And then series and parallel are different ways of wiring something like a battery or like a solar panel. So it's either going to be wired to each other or to something, correct? And then out to the user, and then don't know what.
Oh, prefix is actually not an electrical term. It's just stuff we need to know. Okay, that's pretty good. Yeah. Let's go into more details about each of these. So, okay, this is not a physics class, but just so you know what's going on, like everything is made of atoms, and we have this thing called an electron, which is one of the particles. Okay, so whenever we're dealing with stuff in electricity, it's the movement of electrons. All right, that's all you really have to know. I'm not going to go too much into theory, but that's why some objects conduct electricity and some do not, because the electrons are much more easy to flow and others are not. So for example, wood is not so much a good conductor, but what is? What's a good conductor of electricity?
Metal.
Yeah.
Copper, yeah.
Specific metals though, right? So copper is pretty good, and that's why you see that in the wiring that we use here. But aluminum is not as good of a conductor. So yeah, it depends on the metal as well. But yeah, generally speaking, yeah, most metals are pretty good at conducting electricity. Okay, yeah, I just kind of went straight into that. So if it doesn't conduct electricity, then we call it an insulator. So wood, like I said earlier, plastic, those would be insulators. Glass also. Anyone done inspection of power transmission towers? Do you guys, or you might have seen it if you look closely. The power lines are attached to the tower through ceramic or glass insulators. Yeah, exactly. Power transmission insulators. So
the colors regulate the amount of resistance, right?
Actually, I have no idea if the colors have a significance. I think it's just that's the color of the material. But you can see right here, they don't just attach the wire to the tower. Otherwise, if you touch the tower, you're gonna like kill yourself, right? So they put an insulator there, and they're typically made of ceramic or glass. You can see these are the type of insulators. So I don't know. I thought I might bring it up because some of you might do power transmission inspections with your drums, right? So these are things that they're looking for. Is any of them broken and they need to be replaced? But yeah, that would be an insulator because the metal, the structure, the tower is metal, and metal is going to conduct electricity. So this creates that electrical gap in between. Although it has a physical connection, it's not electrically connected anymore. So that's a situation where we want to have a form of resistance. Remember the board that we built last week? We basically soldered two components on the board. What were they? Yeah, exactly. So resistor it still allows electricity to flow through, but it resists a portion of it. Yeah, so you can think of that as kind of like an insulator in a way, but it's not like a complete insulator, right? But it does kind of resist some of the flow. The wires would be the conductor of electricity. And then we have semiconductors, okay, so that can act as a little bit of both. So silicon is a good element for semiconductor because in a chemical sense, we have a orbital, and it has 4 orbitals. A full orbital is 8 electrons, so it's like right in the middle. So it can give or it can also receive. Yeah. So that's why you hear silicon commonly used in semiconductors. Okay, so if we mention these 3 types of categories, then just understand they basically affect the flow of electricity. Okay, you might have also heard AC/DC. Okay, so there's the band, but it means direct current and alternating current. Okay, so direct current is going to be, I would say the simplest way to think about it is most devices that are end devices, meaning devices that you use. So think about it, your phone, this multimeter, your drones. Those are all going to be running on DC. Current flows in one direction. Okay. We also have something called alternating current, and think of that kind of like a wave, like crashing on the shore. It comes in, but then it pulls out. It comes in, it pulls out. Okay. So current is going to alternate directions. It's going to reverse direction, and it does it very fast. Here we use 60 hertz. So that's hertz is how many times per second. This is what we use to transmit the electricity from the power plant here. Yeah.
Is that why AC is capable of reverse polarity?
Yeah, I mean, there's not really a polarity with AC. It's going to be like, because it's constantly jumping. Yeah.
That's why, I guess that's why it doesn't matter.
Yeah, it doesn't matter. Yeah. Yeah, well, this will still give a reading like a positive or negative. But yeah, there's like, it is constantly going back and forth. Yeah. But typically when you have a reading, that's the reason it's positive or negative is because you have a neutral. So you have one that's hot and then you have one that's neutral. So the neutral becomes like the sink, and that's where the electricity is going to go into. So if you plug the black into neutral, you'll read a positive number, but if you plug the black into your hot, it'll just read a negative because it's going the opposite direction. Versus DC is when you actually see like a positive and a negative side, then there's like a polarity. So in a sense there is a polarity, but not really. I don't know if that makes sense.
No, it kind of does.
Yeah.
It's a tricky.
Yeah, exactly.
It's really tricky.
So with DC, we have a positive and negative terminal. But with AC, it's like source. It's like a hot and then a sink. Yeah. So anyone done commercial electricity work? But yeah, even if you change out the outlet on your wall, if you pull it out, you'll see 3 types of wires. It's going to be black, a white, and then either green or just a copper wire. Just look at this thing. That's exactly what it's wired to each of these. This is going to be, I believe this is your black, which is your hot, and then this is your neutral, and then this is ground. So you don't technically need ground. That's why you see some devices just have a 2-prong plug. But for safety reasons, it's better to have a ground. Yeah. So, but yeah. AC is how we transmit electricity over the power lines. So the power plant generally makes DC electricity because whether you're doing like a coal, nuclear, natural gas, whatever, it's usually creating steam and it's turning a like a generator, all right, and that creates DC. But then they transform it. That's why I say transform. So the term transformer is changing from AC to DC or vice versa. So then they transform it to AC. They transmit it over the lines. Then we have a substation that steps it down. You might have seen it if you just drive on the street. Sometimes you see like these very beautifully gray boxes, and then they have all the wires coming down. So they're stepping down the voltage. It's still AC until it gets to your house, and then actually your house is still AC. So this is AC right now. If I was to plug in, okay, let me switch to my camera view. If I was to plug in this thing to our actual outlet, I need to put it into AC mode. So let me show you. And I need one other thing. Okay, good. All right, so okay. So everything up to your outlet is basically going to be in AC. All right. So AC, if you recall, is going to be the squiggly line. And the reason it's a squiggly line is this is actually showing you the curve of it going from positive, negative. Remember, alternating current. Okay, versus DC current, direct current is like it's just going to stay on one side of the baseline. Okay, so that's why we have this symbol. Okay, so I put it on AC, and then I think I showed this last time already, right? Yeah, but basically, if I put this lead right into the outlet, does anyone remember what a typical?
Almost 20.
Huh?
Shows up as 118.
Yeah, it should be 120. Okay, it should be 120. That's the target, but it's not. So there it is, 117. Okay, I'm just gonna plug this into the other end, and you'll see negative. So I'm just switching it. Oh, it doesn't show negative. Okay, yeah. So I guess in this case it doesn't show negative, but yeah, it's just gonna show you the total differential between the two. Now this doesn't work if I go to DC. If I go to DC, oh, yeah, you see it's kind of freaking out right now. Yeah, so it says 10 volts, but then it keeps refreshing because this is an alternating current. So you kind of have to know. Batteries, on the other hand, these are DC. So I'm in the DC mode right now, and I'm just going to match up the colors, black to black. And we have here 15.4. Now this one, if I switch the polarity, you'll see it's going to go negative like that. All right, so you got to keep in mind, what happens is all the things that you plug, okay, not everything, but for example, some of you have like a USB or a brick. A brick, what I mean by that is this thing. Okay, that's a transformer. That takes your AC, yeah, exactly. That takes your AC and it converts it to DC. So this is a USB like charger. It takes the AC, converts it to DC. On top of that, it also steps down the voltage because you see we have 120 out of here. Your device doesn't run on 120. It runs on, well, at least it charges at 5 volts, okay? So that's a big deal. So it's doing like two things. It's converting AC to DC, but it's also stepping down the voltage. Yeah, okay? This is a visual to show you what I mean. Okay, so if the thing was not powered on, let's say you turn off the electricity, 0, right? So that's our baseline. With DC, when you turn it on, depending on how you probe it, it's going to be on the positive side or the negative side. Okay. AC, on the other hand, you see, if you were to play this like a video, it would keep like bouncing between positive and negative, and they have different. This is like a sine wave, and this is like a square wave. So depends like how you show it. We don't have a way to show how things happen over time on this device, This just shows instantaneous. But if you use something called a oscilloscope, you can see something happen over a period of time. And you can see it like much more granular. Like this one was freaking out because it only refreshes maybe every second. But the oscilloscope would read it in much closer increments. Okay. All right, so now let's actually go over the terms. So voltage, it's going to be the pressure, the potential, the force that pushes the current through a conductor. Okay, so measured in volts. There is a voltage regardless if it's like the device is being used or not. So I'm going to be, I have another slide later, you'll see. I used a water analogy to try to illustrate this because it could be a little confusing. Like, how do you have a voltage if it's not being used? Think of it as like a dam, okay? If you have a lake and you have a dam, there's potential, right? The water is higher level than on the other side of the dam. You're not using the water, but there's still potential. And then if you open the floodgates, then there's still that same pressure, but now you're using the water, okay? So that would be an example, what I mean by voltage. Like this thing has a voltage. You see, I wasn't plugging this into a drone or anything. It has a voltage. A current, on the other hand, that's the flow of electrons. So if you're not using it, there's no current right now. So that's measuring the flow of the water in a sense. So once you plug this into a drone and you start flying the drone, now it's going to draw some current. And the more aggressive you're flying, the more acceleration you give it, the more current it's going to, the current is going to increase. It's just going to draw more water in a sense. Yes?
That's what the C rating is on the
Exactly. Yeah. So if you look at the batteries, if you guys still have it, you'll notice it says 14.8 volts. All right. So that's your voltage. We didn't read 14.8 because battery is going to start at a level and then it's going to drop over time, just like a dam would, right? The water level drops to a certain point where even though there's still some voltage, it may not be enough to, be useful anymore. Now the C rating on here, it says 100 C. Okay, that's basically going to tell you like how much current this battery can handle, like how much it can supply. If you use a low C rating battery on a drone that requires a higher current, you're basically going to like brown out. It's going to try to draw more than the battery can supply. So it's important to size up accordingly. We'll go more into detail on that. Don't worry too much if you don't understand all the numbers on the battery. I'm trying to slowly introduce some clarity because there's so many numbers on this thing. Okay, then we have resistance measured in ohms. So we used the resistor last time. And then we have power. Okay, so power is measured in watts. Specifically, it's going to be the current times the voltage. That tells you the power. Yep. All right. Okay, here is my water analogy. So this is more like the water is your electrons, and this is going to be like a water tower. You see right now, when the gate is not open, you still have pressure. You still have voltage on that gate. But then once you open it, you still have the same voltage, but now you also have current because now there's actually movement of water. Mm-hmm.
Also, as the water would drain down, you would have less weight at the top, forcing less pressure.
Yeah.
Which would be like your current getting lower as the battery.
Yeah.
Right.
Exactly. Your voltage is also going to get lower as you use it, right? Like if you just have a normal AA battery, right? Those things are 1.5 volts each. That's what's supposed to be. If you measure one, does anyone have a AA battery?
Yeah.
Okay. Usually if it's like fresh, they might start off at like 1.6 volts. All right. But then over time, just from experience, does anyone measure their battery to know if it's dead or not? Or you just like chuck it as soon as it doesn't work in that one device? Oh, okay. I mean, some devices are more like picky than others. So what I usually do is like, I will have like this bucket of partially drained batteries that are still like good enough for low power hungry devices. Okay, so if we go here, let's see. This is a fresh battery. Okay, so once again, is this AC or DC for a battery? DC. Okay, I'm gonna put negative to this side. This is how you actually. Okay, you see right here, it says. That's what I was saying earlier. This is like a really fresh battery because it's 1.6. Nominal is 1.5, and usually when it starts to die, it usually is like 1.3, 1.2, and then it's like usually not usable. You notice how it doesn't go to 0 to be dead in terms of device eyes. It just goes below a certain point. Yeah, you have a 9-volt battery here. Okay, I've actually taken apart one of these things, and what happens is you just have 6 1.5 volt batteries in here, like miniature version of that. Just think about that. What's 6 times 1.5? 9. Okay, so that's basically what they did. They just put like 6 of these little things in there. So anyways, this nominal is going to be 9-ish. We'll see. Okay, there it is, 9.56. So it's pretty fresh still. And I think when it drops to like 8.5 or something like that, then it's usually not usable anymore. So yeah, if you have a multimeter, you can actually check your individual batteries. I mean, they all tell you what the rating should be, right? If you look at the battery, it should say 9 volts on there. Yeah. So this is how you can check. Instead of like, let's say you have a bunch of batteries, you're like, I don't know if this is good or not. Instead of like having to plug into some device, you could just measure it on a multimeter. So great. Yeah, so just to reiterate, you'll notice that the battery becomes dead when it drops to a certain voltage, not when it drops to 0. I want to clarify that point. So I guess unlike a gas car, where it's like you're 0 when the gas is out, like you don't really like go to 0. It just becomes unusable voltage. Okay, there is a couple of, I guess, equations to relate these things together. So one of them is called Ohm's law. So if you look at this triangle right here, it kind of relates things. So V is voltage. I is current. This is how I don't know why. I think there's some like probably Latin word or something that means current. But anyways, they use I as current. And then R is resistance. So I is the only tricky one. Yeah, make sure you get the tubes too. Okay. Yeah. You already have a couple, right? I don't know. Do you just need like 3 more or something? Yeah, okay, alrighty. Yeah. Second level. All right. Thanks. Okay. So if we were to do this, okay. So if you look at this triangle right here, if you remember when you write a division, you write a line, right? So let's say you do V divided by I, it's V line I. So if you look at this, it's kind of representative with the line. So V divided by I gets you R. V divided by R gets you I. Or if you do I times R, it gets you V. Okay, so those are like kind of the way to visualize this. So if we look at our example here, we have 12 volts. We have 3 ohms. With those 2 pieces of information, we can find the current. So how are these related? If you look at the V is right here, the R is right here. So how do we get the current then? Okay, divide it, yeah. I mean, it also says on here, but does anyone see, like, you see from this triangle, like, just imagine this line right here dividing the V and the R, literally dividing the 2.
I equals V over R.
Yeah, I equals V equals R. So that's basically what we do here. 12 volts divided by 3 ohms gets you 4 amps. Okay. I'll give another example, just to make sure people actually understand. There, we're going to go here. All right. So let me draw this triangle again. What do we have on the top? V, and then I and R. I think that's what it is, right? Yeah. Okay. Let's say we have a voltage of 16 volts, and we have a current of 2 amps. what is the resistance?
8.
Huh?
8.
B?
8.
Oh, 8? Sorry, yeah. I don't know, sorry. I heard that. So you did, yeah, so you see V right here. I'm going to draw it in red. This is the line that divides the two. So V divided by I equals R. So we have 16 divided by 2 equals 8. And what's the unit of resistance? Ohms, yeah. Okay, good. All right. Yeah, oops, let me just do this. Okay, good job. We'll just do one more. So if I have a resistance of 5 ohms and let's see, a current of 2 amps, what is my voltage?
10.
Yep, so right here we multiply. They're side by side, so here we multiply. So V equals I times R is the same as 2 times 5 equals 10, and the unit?
Volt.
Yeah. Okay. I harp on the units. I'm sure Louis has know too. So engineering school, if you don't use the units, you're gonna lose points because it doesn't mean anything. If I just tell you this thing is 10 what? Is it 10 ohms, 10 volts, 10 volts, 10 amps? It doesn't mean anything. So you have to be very specific. So yeah, make sure that you're using the right units and you keep track of it too. Okay, do you guys understand how to do Ohm's law? All right, so that's going to relate the three: voltage, current, and resistance. Now we have another equation, and I don't know if this one has a name. I just call it the power law. But power is going to be volts times current, voltage times current. That's power. So you might hear, oh, I have a 20-watt system, whatever. So watt is the unit for power. So in order to know that, you're going to have to know volts and current. So if you look at this example right here, we have a lighting fixture that draws 0.71 amps with 120 volts, just like our outlet, applied. So first, and then, let's just stop there. We'll just do the first part. What is the power? 0.71 amps at 120 volts. What is the power? Yeah, so we have power equals volts times amp. So 0.71 times 120 gets you 85.2 watts. Now energy is how much power is used over a period of time. So you guys look at your electricity bill. What did they charge you based off? Kilowatt hours. Okay, so they're charging you for energy usage. So if you turn on an AC, which is typically like 5 kilowatt per hour, okay, then you're going to be charged 5 kilowatt hours at whatever outrageous rate they keep charging us at. So I think it's like if you turn it on during peak time, what is it, like 60 cents per kilowatt hours or something like that? You know, most of the country is like set 20 cents or something stupid cheap. But anyways, we all like living here because it's nice, right? We got to pay for it. So anyways, they charge you for kilowatt hours, okay? They charge you how much energy you use. So if we take that same thing that we use here, 85.2 watts, and then I said we kept that light on for 4 hours. How much energy did we use? So that's taking your power and you're multiplying by time. And then we get watt hour. Watt hour. Now for homes, we use kilowatts because you're using a lot more electricity. That's why I mentioned in the beginning prefixes are important, because this is the same as 0.3 kilowatt hour. 0.3. But in this example, it wasn't that much. It's just a light bulb. It's not an AC unit. AC uses the most electricity in most homes. Just like, I don't know. I'm sure some of you like know if you if you have to pay your own electric bill. Yeah. Okay, so let's do an example right here. So what's our equation for power? Yep. Okay, so let's give us, I don't know, let me give a scenario here. So current is going to be 20 amps, and our voltage is going to be, I'll do nice numbers. Okay, I'll do 60 volts, okay? What is our power?
120.
That should be 1200. Yeah, 1200 watts. Okay, if you run that device time over 4 hours, what is that going to be? For energy, what is the equation for energy?
4,800 kilowatts.
What's the equation for energy?
Power times time.
Power times time, okay? So what is that?
4,800 kilowatt hours.
Yep. Ooh, 4,800 kilowatt hours? Let's just stick to, we'll convert later. It's 400 watt hours, okay? See, this is where the units, you gotta be careful. If we want to convert this to kilowatts now, this is what you do. How many watts in a kilowatt? 1,000, okay? 1,000 watts in 1 kilowatt, okay? Now you multiply it. So that's 4,800 divided by 1,000. 4.8 kilowatt hours. Okay, yeah. So I didn't convert in the beginning. I want to just preserve the units, and then later, yeah, I would say both of these are fair. Both of these are valid answers, right? They're just represented differently. Okay, 4,800 watt hours or 4.8 kilowatt hours. Look at the batteries if you still have it in front of you. What does it say on there? 2.2 watt hours. Okay, let's do a little bit of reverse math here. Okay, 2.2 watt hours. That is in what type of unit does this represent? Energy, good. And energy is power times time, right? Now this doesn't tell you watt, but it did tell you the voltage. Do you see that? Okay. And we have to also give it a time because there's no time listed on this thing. So let's just say, for simplicity reasons, we use this battery to power a device for 1 hour. Okay, I'm just going to keep it like that. We know the voltage is what? 14.8 volts. We are trying to find the missing piece, which is current. So how would I rewrite this entire energy equation? We don't have power. We have time, but we don't have power. But we can... Huh?
Would we divide the 22.2 divided by 1?
No math yet. I just want to set up the equation. Let me scroll up here again. Maybe this will help you out. Look at this. Okay. Look at this. Okay, so we don't have power. So how do we get that? Okay, so power is volts times current. Do you guys agree that? Yeah, you see that's power.
Yeah.
So I just broke that out even more. Look at that. We have this. That's from the battery right here. We have that. We have this. We have that. You solve for the missing piece. Yes?
Why is I current instead of C?
I don't know. That's what I was saying earlier. I have no idea.
I have the answer.
Google probably knows, yeah.
French physicists.
French. There you go.
Who studied it, used it to represent intensity de current.
Oh, okay. There you go. Nice accent. Yeah, usually it's some other language.
Okay.
So I just mentioned Latin because like I just a lot of the scientific stuff are usually like they use Latin based because it's a dead language. so it's not subjected to change. That's why a lot of like terms are used like Latin. But anyways, okay, so we have all this info. Let's solve it. So we have 2.2 watt hours. And you notice I'm going to keep writing out the units because when we cancel, it's going to become important. What is our voltage? 14.8 volts. And our current, we don't know. And then the time is 1 hour. Okay. Do you guys know this, right? You can cross out like the same units on both sides. So what's the same units on both sides?
Hours.
We have hours. Conveniently, it's 1 hour, so we didn't even have to like do anything else. It just solved there. We need to break this out. What does the watt mean? What is watt? It's the same as, huh? Okay, so what is that? Volts times. Okay, thank you. It's all long. All right, thanks. Okay, so what can we cross out? Volts, yeah. You see it's on both sides. So now, to solve this, anyone have a calculator? It's going to be 14.8 times I. I equals 2.2 divided by 14.8. What is that?
1.5.
1.5 what? Amps. That's our only unit left. It should be at least. Okay, so if you use this device for 1 hour, then that means you drew 1.5 amps. Okay, does anyone know if we use this for half an hour, how many amps did we draw?
That's an average, though, right?
That's an average. That's an average. Let's just say it's a continuous draw at that. Yeah.
0.75,
It would actually be, it should be higher. Because think about it, if you used it in half an hour instead of 1 hour, you used it faster, right? So the current should be double, not half.
You're saying we depleted it.
Yeah, we depleted it in 1 hour. Or I mean
We were
half an
saying
hour.
Use, we were just
Sorry.
assuming.
Yeah. So, I mean, if we did the same math, except this time we had a 2 here,
That's 3.
right? If I put a 2 here times 2, actually it would be, wait, did I do that wrong?
If the battery burns up in 30 minutes instead of an hour?
You said half hour?
Yeah.
It's only 0.5 instead of 2.
Oh yeah, sorry. I was like, what did I write with 2? Yeah, you're right. Yeah, I was like, wait, that math wasn't mathing here. Okay, all right. So 0.2. Yeah, exactly. This would be a bigger number. This would specifically, it would be 0.3 amps if it was done, if you use the battery over half an hour instead of 1 hour. Okay, that also logically makes sense, right? If you use the battery faster, you drained it faster. And amps is telling you the current, which is the like the flow. Okay. Let me see. I think that was it for equations. Okay. There's only those 3. Okay. Only those 3. All right. Remember, we have the first one, which is Ohm's law. We can go back to Ohm's law. V equals IR. Honestly, if the triangle is too confusing, you can just memorize this. Ver, okay, V equals IR, and then you could just manipulate things. If you want to find current, you just divide by R. Okay, but sometimes the triangle helps people, so I just put it in there. The other one's power. P equals IV. And then finally, energy equals power times time. Those are the 3. Okay, that all comes into play with our battery later on. So there's a lot more things to think about with the battery too, so I didn't want to overload all in one session. So, any questions so far? All right, let's do a practice. Does someone have a brick or some transformer? I'm going to use that term, right? Can someone give me a transformer, some charger device? Yeah. Okay, I'm going to take this one. All right, we're gonna do another example here. I read here. I'm gonna write down all the information, and then we're going to figure out how to calculate some things here. Okay, I read here. 5 volts, 3 amps. Actually, that's it. All right. This one maybe, it didn't say anything about wattage and stuff, but it's okay. Thank you. Okay, what can we calculate from this? I'll just start here. This is maybe not a bad idea to start with this one. What can we calculate from this? Actually, technically, yes. In this particular case, it's not part of a circuit, so we're not going to calculate resistance. But yeah, you're technically right. If it was part of like a circuit, you can figure out the resistance. Yeah, but it's not going to be useful in our case. But you know what? I'll just do it for like demonstration purposes. I just don't want you to think there's like, I guess, a resistance, because that's like a power source in a way. But yes, technically with this information, let's just calculate the resistance. What? How would we do that? What would it be?
5 equals 3 times R.
And then R would equal
5
5 divided by 3. What is that? It's going to be 1.6 if I believe, if I did that right. 1.66. Okay, 1.66 ohm. You can also write it as an omega. That's what the ohm means. Okay. What's the other thing you can calculate?
I thought it was power energy.
Yeah, power is going to be the useful thing we actually want to calculate out of this thing. So power is going to be what?
Volts times amps.
Yes, exactly. Okay, so what is that?
15 watts.
Which is 15 what? Watts. Okay. That's it. That's all we can really calculate, because it's not like a battery. There's no like a watt hour or something like that.
Why don't they do that?
Hmm?
On those batteries, why don't they do that? Because with cars they do that.
What's that?
They don't calculate, the watt hours.
No, this has the watt hour. What I mean is like that charger doesn't have like.
Oh, okay.
Yeah, because if you plug it in for an hour, it'll work for an hour. there's no limitation on it. As long as the electricity is being provided, it'll keep working. Yeah, so that's why I'm saying there was no marking on that, because it doesn't make sense. This has a finite amount of power it can give. Yes.
So I equals amps and
Yes.
and P equals watts. What does E equal?
E is just energy. It's going to be watt hours,
Watt.
because energy is
That's
power
P
times time.
T.
Yes, exactly. P times T. Yeah, the only letter that doesn't really like intuitively make sense is current. That one is I
So
for
T
some reason.
T is hours.
It's time. So in our case, we're using hours, but if I gave you a minutes, you would convert that to hours, right? Yeah, so it's just time. So I guess keep in mind whatever the time is reported in. Yeah. Typically, though, we report things in watt hours or some version of it, that being like kilowatt hours. Or you might have heard of, oh no, actually that's different. Anyways, drones is kind of weird. We also or not just drones, but we say milliamp hours. If you actually look at this, what is amp? We talked about it. It's one of our units.
Amp
Current.
I.
Yeah, exactly, current. So, yeah. It's a little confusing because they use milliamp hours. So if you actually want to find the the energy, you have to also multiply in the voltage, which you do know, but it's just like they kind of like left that out. So when you buy a power bank, they all show like something amp hours, right? That's typically what it is. Okay. Any questions? Yes.
I've seen energy in. I've seen it expressed as E rather than watt hours. In doing
Oh, okay.
calculating like series and parallel.
Oh, okay. Yeah.
So for our uses, E will be watt hours.
E is just like a variable that I use. Yeah, E is not a unit though. I guess. Yeah, just like V is not a unit, R is not a unit. Those are just variables to represent what the actual number stands for.
Yeah,
So just to clarify, yeah, we're not dealing with VIR we're dealing with volts, current, and watt or power. Those are just the letters I write on here as the unknown. I don't know what it is, right? And you plug them in for whatever you have. Yeah. Okay. Yeah. Okay. You guys been able to access the YouTube videos, right? I posted, so yeah, like it'll show up on there. But yeah, you're welcome to take photos. It's just like it's all on the YouTube videos that I record. Okay, the metric prefixes. This is important because we have already had narrowly missed a mistake earlier, right? Remember this one right here? Okay, so the ones that we're going to deal with the most is going to be kilo and milli. They both mean thousand, but in different ways. Okay, kilo is you multiply by 1,000. Milli is 1,000th, which means you divide by 1,000. So what's an example of besides kilowatt that we already talked about, what's another example that they use killing? Kilometer. It's 1,000 meters. Okay, yeah. Kilobyte. Exactly. Actually, for computers, that's where we start hearing other terms: megabyte, gigabyte, terabytes. Okay, so that's just telling you like how many bytes there are. All right. Now megabyte is nothing. It's all about like you need at least some amount of gigabytes, and now they're doing terabytes on the computers. It's crazy. Yeah. Now on the other end, when you start getting small, we're going to use milli, micro, nano, pico. We're not going to deal with this small stuff because that's like microscopically small, and we're not dealing with that level of detail, but we are going to deal with milli. So what's an example of milli? Yeah, actually milliamp. And most of our electronics from the, besides the motors, is going to be milliamps. Like if you're to like measure the current on any of these like little board things, it's going to be milliamps. Yeah. Yeah? Millimeter. Okay, so that's the opposite case of our kilometer. It's a millimeter. So millimeter is like this big. Okay. Yeah, exactly. So you said millimeter? There's also milliliter too. I forgot which one?
Millimeter.
Okay.
The screw.
Exactly. Okay, there's also milliliters. Okay, yeah. So yeah, exactly. There's these are the different prefixes. So yeah, just keep that in mind. You multiply or you divide the right way. Okay, so this one has a this one needs a unit conversion now. So okay, let's take a look at this. If your circuit uses 1,000, I'm going to write it on my iPad here and then I'll switch over later. If we have 11,500 watt hours of energy, and the power company will charge the following. Okay, so what we did here is I divided by 1,000. So what does that do? Let me show you over here. If we were to try to take watt hours and convert it to kilowatt hours, what do? You have to look right here. This is the unit that we're trying to modify. So how many watts are in a kilowatt? 1,000. So I just wrote it up there for you. So you always want to the reason you do like this is so that you can cross them out. They're on top of each other and they can eliminate each other. So what's 11,500 divided by 1,000? 11.5 kilowatts. Okay, so good. Back to the problem. Oh, so sorry, watt hours. Okay, I forgot the watt hours. Notice I didn't put the hour in this portion. I didn't need to because I'm not modifying it. I'm just shuttling it over and it's just continue on. So the only thing I'm modifying is the watt portion. So that's why I left that out. I mean, I could have put the watt hour here and that would have been fine too, but it doesn't make any difference. So anyways, yeah. So we have 11.5 kilowatt hours. Okay. Here's other examples. 1,000 watts. If you want to convert to kilowatt, on the bottom, you would say 1,000 watts over 1 kilowatt, right? Here, let me write these down, and then I will have you all. Here, let me do this. I'm going to write this down, and then we'll work on it over here. Okay, I want us to convert this to kilowatt. I want us to convert this to milliamp. So how would we do that? So you always have to multiply by something. What's going to be on the bottom for this top one? 1,000 watts. And what's on the top? 1 kilowatt. Okay, these are going to cancel out. What's 1,000 divided by 1,000? There you go. And that's where we get 1 kilowatt. Okay, this next one, what do we put on the bottom? Huh?
0.001.
Okay, let me just put this unit first. Amp and milliamp. I'm just going to start with the units. We want to have our target unit at the top and then our original unit on the bottom. That way these two can cancel out. How do we get from amps to milliamps? What is the relation? Exactly. So there's 1,000 milliamps in an amp. So what's 0.032 times 1,000? Yep, exactly. 3.2. 1, 2, 3, like that. We move the decimal spot 3 places. Okay. So milliamp and kilowatts. So that's an example of using the conversion. Okay, there's only a couple more slides. Okay, hang in there. I know it's a little dry, but it's useful stuff to know. Okay, now we're going to talk about the type of circuit that we build. So there's two types. We have series and we have parallel. Series is basically it's daisy chained, one after another. Okay, so if you look here, let me clarify also. These are standard symbols that we use for electricity. So this is like a battery or a power source, and this is a resistor. I don't know if you recall from last week, I used that exact same symbol. So you see it here again. So this is a battery, this is a resistor. There's actually 3 of those. Okay, so the electricity, it flows around, and it just goes through one device at a time. So that's what we call the series circuit. So when you have a series circuit, the current stays the same, but the voltage is going to be the voltage of every individual section. So section 1, 2, 2, 3, 3, 4 needs to add up to 9 volts. Okay, so that's a characteristic of series. This is an example is your Christmas string lights. Rob, with your LED lights, if you turn it on right now, does a portion work and then the rest is broken?
If I hadn't connected them, yes.
Exactly, because it's a series. Actually, my LED lights right here, I'll turn them on later. That's literally what happens. It works up to a certain point, and then everything else downstream is dead because it's series. So Christmas lights. I mean, you take out one of the bulbs, and then it'll still work up to that broken link. Okay, so that's an example. The other alternative is parallel. Parallel means there's multiple paths to go through. So you can see here, the electricity could choose to go through path 2.7 or 3.6 or 4.5. Okay. Some of you last week when I saw your circuit, I'm like, it's not going to work. Because what happened is I saw a parallel circuit that had lower resistance, and electricity, just like humans, we're going to choose the path of least resistance, okay? So if there's a path that electricity can go that doesn't have to go through resistor, it's going to choose that. And then your light bulb's not going to, your LED's not going to light up because the electricity didn't end up going through it. It's a complete circuit, it just didn't go through it. So that's a parallel circuit. In this case, the voltage is the same throughout, but the current is the sum of all the individual circuits. So it's the opposite of what I showed previously. All right. So what did we build last week? If you remember the circuit, do I have it up here still, or did I draw it on the board? Oh, I drew it up here. Let me see. This is what we built last week. Very simple. What do we have? A series or a parallel? Series. Okay. So what does that mean? Is the voltage the same across? If I was to give these letters A, B, C. Okay. Is the voltage the same across A, B, B, C?
No.
Or is it the sum?
Some.
Okay. And then the current is this is the same. Okay, yep. All right. So maybe this week or today we can build a parallel circuit. All right, we can maybe do something else. And then actually I want you to measure the voltage across the components. Okay, so this is maybe a more relatable image. So you can see one light bulb after another, or the electricity goes through both light bulbs. Okay, so this is the difference. When you measure, I do want to note on a practical sense, when you measure voltage, how do you measure it? Series or parallel? To do series, you have to break the circuit, and I have to become part of the circuit.
Okay.
I always measured parallel, right? Like, look at this. I didn't have to cut this line to become part of it, right? I just measured parallel to it. What is this thing? No, yeah, is it series or parallel? You're right. Is it series or parallel? It's parallel, right? Like I have, if you were to crack open the inside of this thing, there's just a metal bar going down both sides. Okay, so you can have multiple things plugged into it. The more things you plug into it, the more current it's going to start drawing. The voltage still stays the same, okay? So that's why if you start plugging in too many things into a certain outlet, sometimes you trip the circuit breaker. The voltage is still the same, but you have surpassed the current that the breaker has allowed. Yeah, so with voltage, you measure parallel. With current, you have to measure series. You have to break the circuit. You have to be one with the circuit, I guess, what I mean with that. Because current is, again, measuring the flow of electrons through a certain point. You can't be a parallel in measuring. You have to be like that connection point. Everything has to pass through you, kind of like a toll booth, right? You have to make sure everything funnels through, and then that way you can count and how many cars are going through, or in this case, the electrons, the electricity. Okay, so when we later measure, we need to break open the circuit. So I'll show that later, maybe when we actually build something. Okay, so just as a recap, current is the movement of electrons from one atom to another, and insulators inhibit the flow of electrons. Conductors allow the flow of electrons. Semiconductors somewhere in between. We can relate voltage, current, and resistance through the Ohm's law. So V equals IR. Power is watts. What's the equation for power? Huh?
They're next to each other.
P
P times T.
No, power. Power is
I times.
yeah, current times voltage. Okay, P equals IV, and then energy is power over time, which is power times time. Yeah, power. I should say power over a period of time. Okay, there you go. Power over a period of time, expressed in watt hours, typically. Sometimes kilowatt hours. Now you know how to convert, though, right? Now, electrical circuit, we're typically going to have these components. It's going to have a switch, like an on and off, a load. A load is anything that is like basically producing something useful. Not necessarily useful, but it's anything outside of your like power source. So our LEDs is a load. The resistors are a load, okay? And then we have the power supply and the conductor, which is the wires. We can have series, parallel, or ultimately, like all of our devices are a combination of some series or parallel. Just so many of them. Milli and killi are prefixes that we commonly use for drones. Okay. Any questions? No? Okay. Yes.
There's an S on the battery, 4S.
Yes.
Does that have to do with series or what is it?
Correct. So actually, the 4 tells you there's 4 cells in here. Okay, actually, that's a good point. These batteries are basically, you know how I was saying earlier, the 9-volt battery is like a bunch of batteries, little batteries. So it's a bunch of 1.5 volt batteries. So is that in series or parallel for us to add up to 9 volts?
Series.
It's in series. Okay. This thing is a bunch of 4. It's 4 cells that are wired in series. And that's what the S means. So the 4 tells you it's 4 cells. The S tells you it's wired in series.
You can't see it on those ones, but you can
Yes.
see the 3S. Yeah, the 3 little packets right there.
Yeah. So some of the batteries, they have a clear casing on it. You can actually see each of the cells. And they're not going to be like a AA battery. This is like flat little sheets. So that's how you can get those in your phone, right? Like if they had like AA battery, those are just different shapes. But yeah, these are going to be each individual cells. So if you see the 4S, you already know. Okay, let me ask you this then. This is 14.8 volts. We have 4 cells in parallel. What's the voltage of each cell?
You said 4 cells in parallel?
In series. Sorry, did I say parallel? 4 cells in series. So what is the voltage of each cell, theoretically? 3.7, yeah. That will come up later when we talk about batteries. That is like the rating of these. Do you have a 6S? What is the voltage on that? Does it say on there?
22.2.
Okay. Actually, before he repeats it again, what would it be based off 3.7 volts per cell? What's 3.7 volts per cell? We have 6 cells. What should it say on his battery pack? It's a 6S. It's a 6S battery. 22.2? Is that what you got? Yeah. Okay. And then we also have 3S battery. You have a 3S battery, right? Okay, so what would the 3S battery be? 11.1, yeah. So you'll see the voltages change based off how many cells you have because they are wired in series. Okay. I don't know why. Does anyone know? Do you know why we don't have a 5S? I really rarely. I don't think I've.
5S.
We do? Okay.
They're out there.
I don't know why. It's just not really
Don't use
used.
them as much.
Yeah. It's basically like we use 1, 2, 3, 4, and then just a 6 all of a sudden. I have no idea why. Yeah. But that was always my. I was like, you can make one, as you can see. Like, you just add another cell. I just don't know why it's not as common. I don't know. That was just my own curiosity. Mm-hmm.
Why are the batteries in cell like broken down into smaller?
I don't know. If I had to say, it's probably because it allows you to configure multiple types of batteries when you have like a smaller unit to work with. Like you can just keep adding them. Yeah. Why they are 3.7 nominal, I have no idea. That's just kind of.
It's like the production is more modular.
I would think so. Yeah. Basically, you can make your own battery if you want. If you bought your individual cells, you can solder them together, and you can make your own battery.
Is it worth it?
Not really. Not really.
Could it be because like they disperse the energy across all the cells, so it's not all located in the one singular cell?
Yeah, that could be a reason. I'll have to look that up. I actually don't know why they do that, but like, yeah, I would think maybe yeah. I'll look that up over the break, which we can take now. Oh wait, yes, you have a question.
No, just the 5S, so it says 6S is more efficient than 4S or 5S, but 5S doesn't provide enough efficiency over 4S to justify the jump. And
Oh, okay.
it's less efficient than 6S.
So I mean, it is practically possible. It sounds like probably from a economic standpoint, it doesn't really make sense for companies to make a 5S if basically there's not a big enough difference between 4.5 and 5.6, so they just do 4 and 6. Maybe, yeah, that might be that would make sense. It's like, yeah, practically you can make a 5S. It's just you don't really see it. Yeah. Okay. All right. Yeah. Okay. Yeah, we can take a break. 4:05. Oh, awesome.
So I prepared the ends of either side. We're just going to solder.
That's what we're trying to do. We have our simple DC circuit line, and we are just trying to connect positive, positive, negative, negative, just like this, okay? All right. So this is just going to be a simple splice. I'm going to just make some room here. Okay, so first thing, I need a little fan thing. Can we get one of those fan things?
Before you splice anything, you're
Yes.
going to want to put the heat tube on, otherwise you can't get the heat shrink tube on the cable.
Yes, good point, exactly. So these heat shrink tubes, because they're like enclosed, you have to first slip it onto the wire, then solder, and then slide it back to its point. It's not like a tape where you can come back later and you wrap it around, okay? So in fact, I'm going to have to peel this back a little bit more because I'm going to have to slip it downstream a little bit because otherwise there wasn't enough room for it. I'm actually going to cut this heat shrink. We don't need this much heat shrink because the only section that we are heat shrinking is the only section that's exposed is going to be this little. So this is how long the heat shrink came in at least. There is different sizes of heat shrink. So they're all talking about the diameters. So you can see right here, this one was probably like I don't know. This was probably like this one. I don't know if you grab which one.
Yeah, that's...
You see how we were talking about it earlier? There's the wire gauge, AWG right here. So the smaller the number, the bigger it is actually. But this one is probably about this line right here, if I had to guess.
Probably would grab the smaller one.
Yeah, so we actually need to grab 2 heat shrinks because the whole point is we need to isolate the 2, okay? So we're not going to solder the 2 and then put it together in the heat shrink. That's actually like encouraging them to short each other out. We need to slip one heat shrink on one, slip another heat shrink on the other one, okay? That way we can keep them separated. This is what we call an insulator, right? So this is going to help insulate.
That's probably the better
Typically,
size
I'm
we'll
gonna.
cut.
Okay, so here's how we size it up.
Okay.
I'm actually gonna use the original one that you'll have.
Oh, okay.
Okay. Yes. So heat shrink. Yeah. So our wire here is like maybe a millimeter thick, but I'm choosing a heat shrink that is like 2 millimeters because, as the name implies, it shrinks down. So you can choose one that's close to this, but the thing is, typically our solder joint is going to bulge out a little bit. So that's why I wanted to ensure that we don't run into an issue where our heat shrink is not going to slip past that point. Nowadays, most of these heat shrink ratio is going to be a 3-to-1, meaning the size of this opening could shrink 3 times as small. So you could have a lot of like wiggle room. Yeah. But don't go too big, otherwise it's to a certain point. It won't shrink any smaller.
Is there a rule of thumb of how far you want the heat shrink to go from the tip end?
I would say like, so right here is our working end. Okay, right here's our working end. I would say like if you put the heat shrink down here, which is like maybe like 2 inches away, you're good enough. Because the concern is the heat from your soldering iron could potentially start to shrink the thing. So you just want to be far enough away from the heat shrink, from the soldering iron, that you don't have the heat of that start to shrink this thing.
Yeah, well, I'm talking about after the finished product. How far do you want it from where the
User.
yeah, I
choice.
mean maybe like here I would say like at least ½ an inch. Yeah. So I had to strip back this other piece previously. Where's the other free end?
Right there.
Oh, because look, like this is like, my heat shrink wouldn't be able to fit down this. Here, I'm gonna get close.
Okay.
My heat shrink wouldn't be able to get down this, so I had to strip the other end to just give me the extra room. Okay, so we chose. Look at the sizing of the tube, and then look at the sizing of our wire. It's like 3 times as wide, which is fine. We don't need this much because when we solder it together later, it's only going to be about, I don't know, like almost 1/4 of an inch. Okay, so this thing is long enough. So I'm just gonna snip it in half, just like this. This will be more than enough. Okay, snip it in half. And then what we're gonna do is I'm gonna slip it on both ends. That's very important. There's been too many times I spliced things together, and then I forgot to heat shrink to put it. I had to desolder it again and then slip it on. Okay. What I'm also gonna do here, and this is commonly something I would recommend you do. Did you just strip this, or was it already broken like this?
Oh, I stripped it.
Okay.
But by all means, do.
See, okay, so
You might have overstripped.
yeah, what I noticed here is that it got overstripped. It's gonna be hard to see on the camera, but basically, if you look at the thing up close, you'll see that there's still a couple extra strands that was already cut. And when you have that, it's not good because you're basically forcing all the electricity to go through less wires. It negates the whole purpose of this gauge wire to begin with. So when you strip the wire, I would always recommend you start big and then step smaller until just the right one to strip it. Did you use 22 or what did you use to strip this?
24.
Okay, so I'm gonna start with the bigger one. So I'm gonna start all over again. I'm just gonna cut it. Okay, I'm just gonna cut it. So now we have the bare wires like this. And I'm also not gonna expose as much, okay, because those wires are not gonna be as strong as with the sheathing around it. So I'm just gonna expose maybe just a few millimeters, just like this. And I'm being light about it. Okay, I'm being very light. This is kind of my cheat when I don't have something smaller than the existing one. This only goes down to 22. So I'm just being light about it. Okay, there I go. I have the full amount of cable there. I mean, you can also look at the piece that just cut off, and if you see strands in there, you cut too much. You cut too deep. Okay, so same thing once again. I'm gonna come in here just about that much. Oops, I wasn't tight enough, but that's okay. I'm just being conservative here. I'm just going to, there you go, okay? I actually cut a little bit too much from that one, that's fine. I exposed a little bit more than I like to. This is ideal right here. This is the one that I have here on the right is more ideal in terms of how much I want exposed. All right, let me do the same thing on the other one. Okay. Yeah, this one I can tell, once again, it got cut. Hard to see. All right, just trust me that there's only like a couple strands here, and there's still more in the actual. There's still more in the actual wires. So once again, I'm just gonna cut here. I'm just gonna start over again.
In that case, if you went ahead with it with fewer strands, would that make it more prone to failing, or?
It might just. In this case, this is a low current application. LED lights don't use that much current, so the risk is like nothing's going to happen in reality. But if you did the same thing, for example, like on your motors, it could heat up. It could localize heating at that point. Yeah. Think back at your water analogy. Now you're using a thinner pipe, and you're forcing all this to go through. Yeah, exactly. So that's what can happen, and it can fail at that point. Yeah. Failure is mostly through overheating. Yeah. So I'm just showing this here because even though it's not as critical, it's a good practice.
Would that cause the wire to fail or the motor? Where would the mechanical failure be?
It's more like the motor's not going to fail because it just didn't get enough electricity, but it's not going to perhaps perform like it was intended to. And then this would just maybe overheat. Yeah. If anything, the failure would happen here at the joint. Yeah, because it's just that you starved the motor of the electricity that it needed. Yeah, so the motor itself won't fail because it didn't get overpowered, it just under underpowered. Mm-hmm. All right, we're going to turn this back on again. Remember, we set it at 700, I believe. Oh, this is at 800 for some reason. Let me turn this down. Actually, I'm going to set it at 650. I think 700 is still higher than we need to. Yeah. Okay. All right, 650. This is Fahrenheit here. Okay, if this was done properly, the last person should have put solder on it. Do you mind touching the screen to focus?
Yep, sure. Over there.
Yeah. Okay, they did put solder on it to tin it, so that's good. Let me see if I can wipe it off now. Yep, I was able to wipe it off, and now we preserve the tip. Yeah, please make sure you put solder on the tips when you're done. Yes.
Do we have that cleaner? There was a demonstration, that video had the guy using some sort of type of cleaner for the tip.
Oh, you're talking about one of the videos where he had like some, like, I don't have that.
It was like a little glue, and you just said, when it's hot, just stick it in and it looks really clean.
Oh.
I guess
Yeah, this happens every time, but it still works. It's weird. Okay. Okay, cool. All right, now my soldering iron is on. We're going to place this in here.
Turn on your fume hood.
Yes, thank you. Okay. Oh, I need to put this.
I was
I'll
gonna
put
say
the
the heat shrink.
yeah. All right, go ahead and come closer. Yeah, basically, it's like it looks big on
Right.
us, but then
Yeah.
it looks really small up there.
Nope.
Where is the other end?
Right in front of you.
Oh, right here. Okay, so don't forget, we're going to slip on the heat shrink first. Slip on the heat shrink first. Okay, and these two wires, thankfully, they're kind of color coded. It's hard to tell, but this one that I'm holding has a white stripe on it, and the other one doesn't have any color. So that's how you match it up. Otherwise, that's another task you would need to figure out. But hopefully, your wires are color coded to some extent. But sometimes they're not. Then you have to figure it out. Now we want to, you see how they're kind of coming in at an angle right now? We want to like really straighten them up and get them as straight as possible. Because they're going to overlap, that's why we didn't need to cut as much. I'm also going to try to twist these together. Okay. Make sure all the strands are together. Dang it.
You would tin each one and twist them and then tin them each. And then
Yeah. There's multiple ways. I'm just gonna try to twist it right here like this. Dang it.
It's because there's some fan fan.
Yeah. All right. There we go. Kind of, sort of. I should have switched to a bigger tip. This is when you want to use a bigger tip. Mm-hmm.
If you were to forget to put on the heat shrink before, would like electrical tape suffice as an alternative?
It's not ideal, but technically yes. But I've had it where the electrical tape starts to undo itself. Plus, it leaves like this sticky residue, which is like kind of gross.
If you look over on my station over there,
if you like
adjusted electrical tape.
If you're in the field and you had only electrical tape, then it's better than nothing. But like if you had the ability to, yeah, always try to use the heat shrink. It's gonna be better. All right, here we go. I'm just gonna
put on there that little black sleeve.
make sure it's there. You go. I'm just giving it a generous amount of solder. Okay, that's it. That's basically it. Just make sure that, I like to make sure that it completely encompass, yeah, if you come in closer, really close. Yeah, it completely encompass the wire here. So at this point, we can actually now slip this back on. You see, this is actually even longer than we really need to, but it's okay. We could have actually cut that down even more. This is just a fancy, hair blower. There's two settings on it. So we have a 1 line, which means that it's just the low setting, and then we have the 2 line, which is higher temp setting. So I'm just gonna set it to one of them, and if you look closely, it's going to start to shrink down. Okay. I can see the constriction point. I see the constriction point where it was soldered. There it is.
Do you know what
That's
the
it.
constriction point temperature is to start making the heat shrink? shrink? Is it pretty low heat?
It's pretty low heat. It's going to be lower than the soldering.
Yeah.
So you're not going to reflow if that was your concern. Yeah, now it's on there, you see? It's not slipping around anymore. So, perfect. We'll do the same thing on the next one. Slip this on without fraying the wires. Okay. Now, once again, and they have different color heat shrinks, so if you want to be even fancier, you can do one that's red and one that's black, just so later on it's even easier for you to figure out, like.
And if you were to mess up, you would just have to cut it off.
Yeah, so what you would do is you would take like an X-Acto knife, and you kind of like, usually what I do is I cut a little corner and then I peel the rest open. Yeah, because if you try to cut down the entire line, there's a good chance you'll probably like cut the wire as well. Yeah, you can definitely, after this demo, we can practice on your own wires. I would practice splicing like what we're doing right now. This is actually going to be a very common. God, this thing is tiny.
Yeah, like if a motor wire got severed.
Yeah. All right. Okay. Oh my. It's okay. There. It's not a big deal. All right. As long as these line up, honestly.
Yeah, that's all good.
That's all matters. It's just easier to like. It's easier to do that, so that way they don't like run separate. They don't become like random wires like there. Okay.
Doctor, oh, yeah. What was his name, Doctor? Yeah, Doctor.
Okay. You don't want to work on it too long because remember you're gonna burn up all the flux. You notice I kind of just went straight for it. I didn't use like the flux before, yeah, because there is some flux on here. But if you're quick enough, then you don't burn it all up. This one's not as pretty as my other one, but it did the job. And that's the point of the heat shrink once again, is that now we can go here and turn it on for like basically in 15 seconds. I've seen it starting to shrink already. Okay, it's done. You want to try it out? See if it turns on?
Sure, we can connect it to the other. 1 second.
There is another repair we'll do on this in a moment, but let's just first see if this one works. No, we could have put another heat shrink here and then like heat shrink. Yeah, but sorry.
No.
See, we forgot now, so if we wanted to do that, you would have to undo both, but I don't think it's a big enough deal to. But in this case, this is electrically safe now. You see, these are isolated.
You're putting them map over it.
Yeah, it's just because these are like split right now. That it would only be more for like organizational purposes, not because.
That's not powered. That's not plugged in.
Hmm? It wouldn't be a problem. Yeah, these are already all like individual. Here, you just unplug.
Oh my goodness.
All right.
All this stuff falling.
Okay, we're gonna unplug the computer for the time being.
Okay.
Let's use this. Look at that. This is on both sides of our soldered component. So, beautiful. It works now. See, here's our solder joint, and both sticks are working. All right. What is this? Is this another problem down
Yeah,
here?
that's another.
Okay, so he's gonna do this later on in his own. Yeah, so this is not as ideal, but now that you know how to solder and how to do heat shrink, we're gonna get a nice professional looking connection. And then one of these is broken, correct?
On each, you got the right there, right. No, right. You're holding it right here.
Oh, okay.
I don't
Okay,
think you're
I
going to
see
be
what's
able
up.
to. Yeah.
Okay, so this one got severed in the tube. This one's going to be tricky because with these LED lights, it looks like we actually have.
And it changes along the board. Now that you've pointed out the board to me,
Actually, you know what? This may not be 4 wires. Initially, I thought it was 4 wires. The reason I said 4 wires is because there's 2 coming in and there's 2 coming
going
out.
Yeah.
But really, I think there's only 2 wires going down the line. Because as you saw, LED light, you just need 2 wires. So this actually might be simpler than I thought.
so I can probably just jump the 2,
Yeah.
pull from the top.
I always say that with caution, though, because you think something is simple and then it really isn't.
Yeah. I was like, can we just wire?
Okay,
2
so what we
points?
need to do is...
Unplug it.
Yeah, well, first unplug it. But what we need to do is, this is going to be more, I would say, like a more advanced repair. Just because of how tricky it is, that's what makes it more advanced. So you're going to have to come in pretty close for this one. Does anyone have a knife? Oh, okay. You mind if I use it? Yeah. All right, thank you. Okay, so this is a circuit board. Inside, there's multiple layers on this thing. Inside, there is like a copper connection. Now, these are covered right now.
I was gonna say it looks like a single surface with a solder mask on it.
Yeah. Yeah, so these are covered right now, so you can't see the copper connection. So what I need to do is I need to scrape away the coating, and then I can access the copper inside.
Having worked in circuit boards, that's solder mask.
Solder mask, okay.
And then you'll just solder the copper.
Okay, here's what I'm gonna do. Here's what I'm gonna do before I actually do that. Let me put
I
this
was
knife
wondering.
away.
I was wondering if you could just
Oh,
jump
okay.
it.
Yeah, I think
Yeah.
we can actually jump it. That's what I was about to do. I'm like, okay, here's what I'm gonna do. I'm gonna take one of these. Okay, let me ask the audience. I'm gonna ask the audience if we wanted to confirm that these LED lights are connected. How? Yeah, there you go. Yeah, you got it. Okay, so let's see if these are connected. I'm gonna use the continuity button. Okay, so I set it to this. I set it to this, and then I changed the function until we got to continuity. Okay, and then I'm always gonna, can't really hear, but I can hear up here that it is indeed making a noise when I touch it. So let me just go to here. Oh, they're connected. That's good.
So we can
So
just jump
so
the
this
wire.
makes things a lot easier. Even though they are there's going to be electrical connection within the board. What we're going to do is we're just going to jump this solder joint to the next solder joint, and then we're done. So what we need to do is get 2 pieces of wire. Oh, look, we have wire.
Oh.
Okay, you have wire too?
I was like,
Oh,
lift
white
up.
wire is even better. How about that? Then it'll blend in a little better. Okay, so do you want to give it a shot? Or, no, I'll do the
Go
demo.
ahead.
I'll do the
You
demo.
go.
You have another one that's broken, right?
Oh yeah.
You'll do it on your one. Okay, so first thing again. So actually, I don't need the knife, but I appreciate that. So first thing again, I'm going to strip away this wire. I'm going to start with the bigger end, and I'm just going to strip away a little bit. So if you notice this one's a little different from the other one. This is actually a solid core wire. This is nice because it holds a shape. Yeah. But it's also not as flexible as the other ones. So in our drones, we typically use stranded wires. But the solder wire is much nicer to like keep things together. So anyways, in this case, it doesn't really matter if we use solid or stranded. Okay.
Other end. That end. That's the broken end. I think. Oh no, you're
No,
right.
this is the free end.
Free end. Okay.
Okay.
I'm so wrong.
That's okay. All right. Let me just do this. Let me just solder it on because I was initially gonna cut the piece and then like also strip it. I guess I could. It's just nice to hold it from the longer end. I'm just doing it for that reason.
Yeah.
We can strip it down later. For now, I'm just going to mount this like that. Oh my gosh, this thing is like. There we go. Okay, you see, this is why we can't put heat shrink on this one. This is why we don't want to expose too much wire. In fact, I still have a little bit more than I like to. I'm going to just cut this slightly. Okay, that's better. Because of the proximity between this wire and the next one we put to it, you only want to expose whatever is necessary. There you go.
Would you still call that a pad that you're connecting it to?
Yeah. It's actually a through mount because the LEDs came from the back end through a hole, but I'm just kind of like using it like a pad in this case.
So you basically want as much wire exposed as the size of the pad?
Yeah. Yeah. So let me zoom in here. Okay. All right, I'm gonna put some flux on there. Look at the headlamp, by the way. It's a lot easier to see as well.
Don't kick that so you don't step on another board.
Yeah.
This is the other one that's broken?
Yeah, and that's the one I'll fix later.
Okay, here we go. So I put some flux on this because we're dealing with an existing joint. So I want to make sure. Remember, we're heating the joint, not the wire, or not the solder. So I'm just slipping. I'm slipping the solder in though. There you go. Okay. Let me just make sure it's connected. I can once again test the continuity. So what I do is I could touch this end of the wire, and then I could touch anywhere along this side. Oh. No. What's going on? Did this?
Oh, is it because the clip is on the...
Yeah, I was thinking maybe that might do it. Let me try that. That should still work, no? Okay. Interesting. Okay, let me go back to square one. Let me just test some of these. Oh.
Oh, it alternates.
Oh my goodness, are you kidding me? Some of these alternate. Wait, let's think about this.
That's my guess. Yep.
No, these are connected. No, I can actually see the lines right here.
Okay.
No, these... Oh, this is weird. Oh, I see what's up. They're in segments. Okay, you can't see on the iPad, but I see there's a segment right here. I need a marker. If I had a marker...
Actually, if with the headlamp, it actually highlights the...
Yeah, you can actually see the lines.
Yeah.
I
when you
see
get
right
it.
here, it ends right here, and it goes all the way along this line to right here. So this is a new segment. That's why we didn't get it to ring. But it should ring with all of these ones. So if I click here... What? Oh, this is
It's
another
segment.
This is a new segment. Actually, that's gonna be fine.
Yeah.
That's gonna be fine. Okay, I can see
that's within
I can
the
see
same
right
segment.
here that it ended right here. Yeah, this is a new segment right here. This is Okay, let me check the other one. Is this the other one's the same situation where they have segments?
Yeah. Yeah.
No, the other one must be like the negative, so they're all connected on that side. It's kind of weird.
Interesting.
Okay, interesting. All right. Well,
We'll connect and we'll see if it works. If it doesn't
yeah,
work,
we'll just
then
see if
doesn't
it
work.
works. Where's the little piece that goes over there?
So it's on the... Right there. Right there. Yeah.
All right. Before I do that, I'm just going to solder this end too while I'm at it.
Oh, and then clip them.
Yeah, and then I'm gonna clip them. Yes, I'm not gonna keep them like connected like I have right here. I'm just gonna solder it and then I'll clip it later. This thing is driving me nuts because it keeps coming loose. This is like cheap. Like he has a much better gripper thing.
Yeah, that's what I was looking at buying one.
Yeah.
Everybody likes your gripper, though. What is it?
Well, this is like.
Well, I'm used to
this
having
is like
four.
$5. That's like
Yeah.
40 or something like.
Oh,
Yeah.
it's
See.
like 20.
Oh, is it just 20? Okay.
Yeah,
What is it called?
10.
Just look up solder gripper. You'll probably find something like that. On
You can look
Amazon.
up Helping Hands.
Helping Hand. That's right. I should have known better the actual term that I've been telling everyone to use. Okay. Put some more flux on there.
It doesn't move at all? It's pretty solid. It doesn't move around.
I want to make sure it's not hovering, but it's actually like sitting. There it goes.
There you go.
Solder. Okay, cool. Once again, I'm gonna solder the joint, and then I'm going to come in here with my solder. Done.
Done.
All right. Now we can do. I'm just gonna clip these ends right here. We don't need it very long because this is literally supposed to be one after another. Okay. Now we will have to eventually mechanically join these, so I don't know if you have like Gorilla Glue or something like that, but
I have some E6000 at home.
yeah,
That'll work.
there's actually technically you don't need to mechanically join it because it's like in a tube, so
Yeah.
even if it's like kind of hanging, it might be okay. All right. There. See if I could do both at the same time. Give it a healthy amount of flux. Oh my goodness. Alright. It's just, oh no. Okay, that's a bridging.
Oop.
That's not good. But I'm just gonna, see that's what happens, I put too much solder on. Okay, I just kind of removed it by going like that. So that's a cold joint. It looks good, but it's not. You see how it's kind of like, it's kind of like dull color. Let me put some more, flux. I'm gonna reflow it.
Working on a bomb. I'm gonna slowly walk away.
Put some more reflux on. Yeah, sometimes you have to like wipe away the old flux. We'll get some new flux on. Okay, it's good. I'm just like being super particular.
Yeah.
Okay, let's try it now.
So if you plug it in, it'll either work or it won't.
Yeah. Okay, so it's still mechanically like bounded, but it's really holding on by its wire, which is not meant to be a structural component, but
Wherever we're up here, right? Oh yeah, there we are.
okay, you can zoom out from the. Okay, let's see if this works or not. Sorry. Oh, interesting.
Interesting. It only went to the.
It only went to that next one. Oh, that's where the other
That's-
wires are going. The other wires are connecting
Connecting.
farther down.
Oh well.
So okay, I mean, I guess if you look closely, like that is why we have all these little lines.
Mhm.
So what you would have to do is you have to scrape away and then like solder each of those. That's gonna be a pain in the butt. You can try it. We regained one additional LED light.
And the other one was broken higher. it might
It's broken higher or lower?
higher.
So that's actually worse. Yeah. So if it was broken lower, then you would
It would
only
be
have
easier,
these.
but
okay. Well, anyways, this
We
as
try.
you can see is like there's the way it's set up. It has multiple circuits. That's how they can create the icicle effect because they have to tell like certain ones to turn on later. If this is all purely series, they would only flash. So, anyways, that makes sense.
So wait a second, why did you only get one item in that?
Because they break it up into segments.
Let's see if we
So
can
if we
get,
actually look at this, this is one segment. This is another segment. If you zoom out.
I was like
oh, okay.
zooming in so you can see the line.
Yeah, let me show them the lines. Yeah, so you can see there's actual individual lines here. So those divide this thing. It looks like this is designed to be segments of 3s. Because if you zoom out to normal again, you can see this segment is basically flashing at the same time. This segment is flashing at the same time. So they have multiple wires in here so they can tell segment 1, segment 2, segment 3, segment 4, turn on one after another.
So you simply didn't wire the segments.
No, well, we thought it was like, oh.
We were hoping.
Yeah, we were hoping like it was like all series. It wasn't. It's like, okay, let me count this. 3, 1.
Shouldn't there be a wire, an additional wire conveying additional segments that should be connected to it?
Huh?
I mean, it looks like all they want multiple traces.
Well, there's a
Okay, so there's a chip here, and this chip basically tells the incoming wire. Yeah, there's only. Okay, ignore the fact that there's 4 wires. The reason there's 4 wires is this is in series, so it comes in and then it goes back out again. But what it does is we have this chip that tells it, hey, distribute the electricity to segment 1. Wait half a millisecond. Or
Hey,
It's me. How did I hear that? Thank you.
who's what?
Nope.
There he is.
There we go.
it says distribute electricity to segment 1, then wait 100 millisecond. Distribute to segment 2. So I tell you, the amount of LEDs in here is probably a multiple of 3. Let me see. 3, 6, 9, 12, 15, and 18. That makes sense. So basically there's 6 segments and it's telling segment 1, segment 2, segment 3, segment 4, segment 5. That's how it can create a cascade effect. It's doing that. If it was what we were hoping, just a simple series circuit, it would only flash everything at once.
To relate this back to
Yes.
drones, that's a PCM,
Power, what's
power
that?
control module.
Oh, okay. Yeah, basically. Yeah,
Does that mean
exactly.
it's parallel then?
So this is actually, here, thank you. That's actually a good question. This is actually a series of parallel and series circuit. If I was to draw this, let me show you what's actually going on. So what's going on is that we have 6 segments. So turn it this way. We have
They have 6 groups of series.
yes, exactly. So here is grouping 1. Okay. Then I'm going to duplicate this. Is that 6? Okay. So you can see right here, we have our chip here. And all of these are connected to this chip. And then this has to go back to power. Yeah, this basically, these all still connect to, still connect like this in a way. This is the negative and this is the positive. That's why earlier I was running down one side and everything beeped, but the other side only beeped in groups of 3. So what you see, here's our series within each grouping, but then they're all parallel to each other. So that's what's happening in this thing. And this board right here is just distributing the timing of when each of these turn on one after another.
How do you fix the subsequent?
So what we did, we just thought, we imagined this thing was just like one after another. So to fix this, you would have to, okay, I'm gonna draw the board. This is what it looks like. Inside, inside this is like the actual LED light, and then we have a let me do this. Let me draw segments like this. Let me draw. Darn it. Let me restart. Let me. Here's segment 1, segment 2. Okay, I'll start with that. Here's A, B, C, D, E, F. So this right here is segment A. This is B. So how they're connected right now is like this, okay? They're like this. So this is like, let's just say this is your negative and this is your positive. Then we have another one like this. They're all connected through the negative, but this is like positive for A, this is positive for B, and then we have a positive for C. So what you have to do if you want to actually fix this, you have to take that knife, you would have to scrape away at the board, expose each of the lines to each of the 6 segments plus the ground, and then solder. So that means we're going to actually have 7 wires you would need to solder, which is going to be really difficult because, I mean, it's a challenge. You should try it. Actually, not 7. I take that back because the first 2 is okay now. So you would just have to do, how many more segments do we have? We have 4 more segments plus a ground. Actually, the ground I've already connected because one of these is actually valid. So we just have to do 3 more. Not the worst thing in the world, but you're going to have to deal with the 26 gauge wire that we have here. I think we used 22 gauge wire here. So you're going to have to use that one. Give it a shot. But, yeah, let me see, PCB board wiring. Let me just show you in case you may not be visualizing. This is what's going on. This is covered in a film. That way, it's basically like the heat shrink, so you don't short something. But by taking the knife, you scrape away the coating, you reveal the copper underneath, and then you would like solder your little wire onto it, your jumper wire.
Most PCBs use a green solder mask like that.
Solder mask, that's the term.
But you can get it in almost any color. Some are blue.
This is white in this case. This because it's like an icicle, so I guess.
It's cosmetic, but it's cosmetic but functional. Like,
Why is it green? Do you know why it's green?
Why is what?
Green.
It's probably the cheapest.
Okay.
I used to work doing that as a teenager.
I see.
My parents did that. They met at a printer circuit shop. So like, as I got old enough to do any kind of job, and learning like the inspection points, like continuous versus. But the solder mask is sort of the last step you do after the board is almost completely done, and then you test it again to make sure that everything else.
Yeah. So you want to try the rest?
When that got snapped, it broke the copper connection on the PCB.
It broke the PCB board, which has the copper connections within it. So yeah. That's why it's pretty hard to fix like a lot of our electronics because they're so tiny, and it's not like you just cut a wire; you cut many wires. Yeah. Okay. I also have here another example of that type of thing, but a lot easier to work with because like these are much more coarse. So let me show you. Who wants to come up and try? I guess. Want to come up and try? Okay. Let me first pause this recording. This is intended for you to cut. It even has a scissor mark on it. And how you connect these is just by what we just did. A simple 2-wire solder. Because this one doesn't have a chip that segments this is all or nothing. Look, I turn off the power, everything turns off. So this will be simple. And it also told me this is 12 volts. So that's why I only set it at 8 right now. But I can crank this up to 12 and it should be okay. It just gets brighter. But that's where, if you look down here, this is how I connected it. I just wired it straight up to the thing. So, anyways, that's how I can test this without having to like plug it into a compatible plug. I don't even have this plug with me right now, but we're able to tap into it. Okay, this one is obviously okay. So some of these are broken, I know for sure. So we'll find them soon enough. Let me grab this next one. Maybe this is the broken one. I think one of these were broken. Here we go. Too many stuff. Now, if you didn't have this plug, I could always read this thing. And it says what? Output 12 volts at 3 amps. What we care about is the 12 volts. So I could just set this thing to 12 volts and it would work. But we happen to have a transformer right here, so let's just use it. It's a lot easier. Okay, I'm gonna plug this stuff in. All right, this seems to be working. I can see the LED lights light up all the way in the center as well. So this one was okay. Where's the good pile? I should put a good pile. This is the good pile. And then the other one that I just tested, where is that? Oh, it's on the ground now. Okay. All right, so these two are good. All right, let's see.
Hey, Han, do you know where I can find a wrench?
Try that tool cabinet. Okay, this one's broken on the interior. You see that? We're gonna fix this one. Because why do you think it's broken? Is it a series or is it a parallel?
Series.
It's a series, correct. Okay, let's unroll it and find out what happened. Hey. Oh, I see the issue. Look at this. This got screwed up. So, here's what we're going to do. Okay. This is an RGB light. You see how now we have 4 pads that we can deal with? Go ahead and just touch the screen.
Oh, so focus.
Yeah. Okay, we have 4 pads. I'm going to turn it around so you can read the letters. It says 5 volts GRB, or RGB is more commonly known. Okay, so that requires us to solder 4 times. This one is not segmented, but it is a multicolor LED. And if you only had 2 wires like we did in the past, there's no way you can tell it to change colors, right? So that's why we need additional wire. Let me see, I think this thing does it. Where's my little... Oh, it's down. Oh, it's right here. Okay. Okay, well, it's supposed to change the colors. Oh, you know what? I think I put the little battery like stopper thingy so that it doesn't chew up battery. Okay. Oh, there you go. See? It changes color. And I'm pressing different colors: red, green, blue. Okay. Yeah, so it's sending the signal accordingly. I bet you if we were to take a multimeter to this thing and measure the B for blue, I should see a reading on the B, but I should see no reading on the R and the G. And then if I get the red, then it should do the red. If I did something in between, what's in between red and green is, or let's just do yellow, for example. If I did, that's not yellow. That's a lame yellow. What is that? Whoa, something's up. You can see something's up because look, it's like one end is blue, the other end is green. Well, obviously we know something's broken. Try purple, yeah. Okay, yeah, see, this is like purple, but then, interesting. Something happened here. It went from like red to purple. Oh, we have another break. Oh, look. It's very temperamental. You see, it sometimes works, it sometimes doesn't. So this is it's another tear. We have a tear in our strip. Okay, so we actually need to fix this in 2 spots. Great. Okay, so what we're gonna do is we're actually just gonna cut this. I mean, it's gonna be the easiest to just cut it because we have access to the pads. This is nice because we have access to the pad. I'm gonna get really close here. If you were to try to scrape it away, it's super thin. It's like less than a millimeter thin. Look at the one where our tear is. So let's just go to the pads where they thickened out. Okay, so what you do is you just cut it. Yes. So let's see where our 2 tears are. We need to wait. We need to find the next pad section. Here's a pad here on my right thumb. Here's a pad on my left thumb. So what I'm going to do is, yes, we need to cut basically in between. You want to preserve both pads, and then we can put this together. Okay. So I'm going to cut like right here. Because our tear is right here. This is where our tear is. So in between 2 pads is where our tear is. So I'm going to unplug it first. All right. Unplug it. I'm going to cut it right here. Okay, that's fine. I'm not, yeah, you could cut on the pad, but I'm actually, let me think about that.
I was like doing LEDs, so there's connectors for this. Generally, you cut them on the pad.
Okay, I was thinking of connecting later downstream, but yeah. We cut it on the pad, right? Cut it on the pad. Okay. I'm going to preserve as much of the pad as possible. So instead of cutting like this, because the portion that we're keeping is the top half, so I'm just going to preserve as much of the pad as possible like this. Like that. Oop.
How frequently are there pads?
In this case, it's like every this length. I mean, it depends on the manufacturer. So, okay, our tear once again is right here. Oh, switch it. Just go to photos. Oh. Okay, our tear is right here, so I'm going to go to the next pad, which is right here, and I'm going to preserve once again as much as I can. So I'm gonna preserve by keeping as much pad on the line that I'm keeping. Oops, I didn't even. Let me just like. There you go. Come on. Okay, there you go. I have. Okay, here's one pad. Here's the section that I removed right here. This is a section that I removed, so if someone cares for 4 functional LEDs, you can... Actually, this is a good one, Rob, if you want to practice like scraping away and soldering, you could do it on that one, actually. Or someone else wants to do it. Okay, anyways, we have our 2 pads now. You see right here? Yeah, I know it's hard. We have our 2 pads now, so now I'm going to solder them. Man, I wonder if I can do this without even wire. Can I just use a little bit of solder? Yeah. Yeah, let's try this. Okay. That would make things convenient, wouldn't it?
And you do it on both sides?
What's that?
Do it on both sides?
No, you only do it on one side.
Okay.
But for me to do like a straight one, I have to cut it pretty much at a 90-degree angle. So let me fix this one because it was cut slightly at an angle.
Would it be better if you cut them both at the same time? Or just splicing a tape?
Oh. Yeah, I guess I could. Yeah, this is okay too. Okay. I just trimmed it a little bit. Okay, we need to, also important, you need to match up the letters. So let me make sure I match them all up. Okay, there we go. Yeah, let me just check. All right, let's.
Suggestion?
You want me to put something
What's
under
up?
it and hold it?
Once
You
you
mean hold it up
rest it
there?
on this,
Yeah, thank you.
That's exactly what I said.
That's pretty good. Thank you.
before I finish putting this back together. I was thinking.
All right. Solder, flux, line this up.
Power.
Once I get my first joint on, it won't be like moving all over the place.
Do you have to worry about the heat messing up with the rivet?
What's that?
Will the heat mess up the rivet?
If you dwell too long.
Okay.
So that's the general case with all of our soldering. Don't dwell too long. Just get in there. You notice when I'm soldering, I'm pretty quick. Uh-oh. Yeah. Damn it. We might need a wire because the solder, like, it's not meant to be a connection medium. Oh, wait, care. Oh, there it is. It's not meant to be a connection medium. It's meant to be a like a glue. You don't use glue to like structurally hold things together, but that's where I. Anyways, okay, so I got one. Let me see if I can get the other. Oh, the other. It's kind of shifted a little bit. All right, let me see if I can get it. Anyways, see, this is where it'll be nice to get a fine tip, a finer tip. Should have changed it. Oh well. So I'm trying not to also unbridge the other. Oh, there you go. Oh, that's a tiny one though. I might have to go back to that one. Come on, there. Ugh, that's a fat one. No, I don't like it. I don't like it. I'm gonna have to undo that one. No, it's not. It's too much. Oh, that's better. That's better. Okay.
Bridging, huh?
They're not bridging each other. We can double check though. Come on.
Is it bridging?
No, I think it's good. Let me just put a little bit more on this one. Beautiful, beautiful. All right, let's just double check that we are not bridging each other, that is. And I also want to double check that we are on both sides. So let's do both. I'm going to once again set to continuity. I'm gonna touch each of the exposed sides and let me listen. Good. 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 To be really sure, I should go somewhere farther down line and check because that might have just been me touching the solder and not actually around the pads. So I'm gonna go here to the B and I'm gonna go B, good. I'm gonna go to the R, good. G, G, good. And finally the 5 volt. Now, I tested to make sure that I bridged. Let me make sure I don't touch adjacent ones. Okay, come closer, yep. So I'm gonna touch the adjacent ones and there should be no noise. We don't want noise. No noise. And no noise. Good. All right. So now this should be safe to turn back on again. And let's take a look. Beautiful. It works. So same thing needs to be done on this line. If someone wants to give that a shot, I'll hand this off to someone else. This one right here. Okay, I was gonna say we might want to put some heat shrink, not because it needs to be electrically connected, but because this is kind of a weak joint right now. And I don't want it to break again. So what I might actually want to do is get a little piece of plastic. Shoot. See, this is an instance where I didn't put the heat shrink on. I should have done that earlier. But it's okay, because I can unplug from this end. So this is okay. Let me see if we have a...
And then do like a
Do you have a heat shrink case? Oh, yours is up here. So I'm gonna grab the widest thing we have here, which, oh darn, it would have been perfect. Okay, this is just slightly too small for this opening. Oh my gosh, but it would have fit if I slipped it on earlier. I'm gonna have to do the hard way, which is to literally unspool this whole thing and do it the other.
But you're gonna fix the next one when you trim that.
You're right.
Yeah.
Okay, you're right. Okay, the next one, someone who does it, we could do the you could do the slip on the heat shrink.
Yeah,
All
put
right.
on 2 pieces of heat shrink.
Thank you. Although I've already unspooled half of this thing at this point. Okay, so I actually have a couple.
Okay, isn't it?
All right. Anyways, I think it'll be fine. Go ahead and place that split behind, and then slip the heat shrink on top. There you go. And then keep putting the heat shrink until it covers, and then if we touch down, and we don't want any of that plastic split showing, so tuck it in. It doesn't show on the other side, right?
Barely.
Okay, and then is the solder joint in the middle? I feel it.
Yeah.
Perfect. Go ahead and heat gun it.
Your feed's not live.
Oh shoot. Wait, don't do it yet. Okay, go ahead and heat shrink it. Just watch your finger. You might want to hold it on, or I can hold it.
Did you want to videotape the
Yeah, I'm doing it right now.
other part of me
No.
threading it?
Oh, was that live when he threaded it? Oh, yeah. Let's thread that part.
Okay, let me put this down. Oh, ooh.
Just slide the whole thing off. Yeah, there you go. Perfect. So we put a split back there because the solder joint is weak, so we don't want to break it again. And then we're gonna slide a heat shrink on top to seal it all in. And then he's tucking the split so that none of it shows up from underneath. That way we don't crease the line in the future. And you double check the solder joints in the middle, and then go ahead and heat shrink it now. And then flip to the other side. Beautiful. I think that's it. You can turn it off now. All right. How does it feel? Does it feel like decently strong?
It's still cooling. It's still.
Oh, it's still cooling. Okay. All right. Some drone that's available on the market. So in this case, it's the DJI Flip, and just listing out specs. So I think this was pretty straightforward, right? Like everyone, I think, basically got it. And we all know how to export as a PDF now. Okay, alrighty. Yeah, if you didn't, I wouldn't be able to see it. Any questions on this one? There's no point me like going down the list. I think I just want to see if there's any particular, I guess, spec that you're not sure what it means. No?
The only thing is something towards the very bottom.
For the bottom. Oh, this is actually down here. This is actually quite applicable. Maybe we could talk about this. If we have, all right, yeah.
It was the actual charger. I couldn't find the information on the one that I had.
Yeah, and sometimes they're not going to publish it if it depends on the manufacturer. But this is actually a good exercise right here. We can look at here, right here, the rated power and the voltage, and we can figure out what from that.
The current.
Yeah, exactly. So we have our power, P equals IV. What is the P? Yep, which in this case is 65 watts. And then our current, I don't know. And then our voltage is 7.16 volts. So I is going to equal 65 watts divided by 17.16 volts. Remember, watts is the same thing as volts times amps, right? So we can cross that out. What's 65 divided by 17.6? Okay, 9.08 amps. All right, so in case you want to know, that charger, like our chargers are all rated at a certain wattage. If you look at some of your other bricks, they'll at minimum put a voltage and a watts. Sometimes they're nice enough to also put the current. And if you multiply those two numbers, it should add up, or they should be, the product should be the power. Okay. Yeah, that's it for this homework assignment.
Question on that.
Yes.
A lot of times they'll list the polarity for those barrel plugs.
Mm-hmm.
Is there, because I never really seen this something where that's applicable. I mean, we do have to pay attention to that.
Oh, yeah, I mean, I guess sometimes maybe some manufacturers might switch the polarity. But yeah, there's typically not much you would need to worry about, especially if you're buying something off the shelf. It's already been designed so that they'll match up. But maybe perhaps if you're building your own thing, or let's say you are powering it up from like a power unit like this, you would need to know the polarity of the barrel. Yeah. So I would think that's probably why. Yeah, you're talking about something that looks like this. They have like this thing. Yeah. Yeah, and then the plus minus. Yeah. I know what you mean. Yeah, I would think they only put that because maybe there's not a settled convention on it. Otherwise, normally I don't see why they would need to do something like that. Yeah. So these are the barrel connectors if you guys aren't familiar. It's these types. Yeah. So I see it right here actually. This one says that the plug itself, it drew something like this. And then this is like the negative. So that means that the outer side is negative and the inner is positive. So, okay, any other questions on the homework 1 drone specs? Okay. This is the other homework, which was now you have to find a drone like that has individual parts that you can purchase. So this is basically what it means by like this is basically an FPV drone. So let me see if I was to Google this drone right here. All right, so this is the drone, right? Is this the one you're looking at, Matthew? Okay. All right. So we should be able to. Oh, this is nice because it actually legit is. It gives you options, so you can just like copy and paste each of these. TBS Tango, by the way, this is what we have in our drawers. Yeah. So if later you are to use one of those, wow, it's more expensive than I thought it would be.
They're overpriced. Don't go with the Tango.
Okay. Yeah. Oh, we have the TBS Boxer. Sorry. No, we have the Radio Master. Sorry, not the TBS. We have Radio Master.
You have a Boxer?
No, we have it right here.
Oh, okay.
It's in the drawers. I think that's the one we have. Can you open the second drawer,
I haven't
Luis?
showed off my
No.
transmitter. I have a Boxer.
Down there,
If
the big
anybody
one, the
wants to
big
take a look at
drawers.
that one too.
Which what type of transmitter is it? Radio Master what?
I think you have Zorros.
Oh, Zorro. Okay, all right.
Zorros.
So never mind. They all look like game modules, so like I kind of got.
It looks like an Xbox.
I kind of got confused.
Essentially.
We actually have this one, the Hota D6. It's actually right there on the table. You can see in the black box with the orange border. Yeah, there it is. That's actually what we have. Dang, it is overpriced here. You can get that thing for like 120. I don't know. Maybe they take advantage of the fact you're trying to buy it as a set. But okay, so here they should list the individual components. I can see right here they have individual components, and then Matthew, yours. Yeah. So let me just see if things make sense. This is what I did. It's like you should have 4 motors. Okay, good. I see 4 motors. Typically.
These prices, do you think they're post-tariff? I mean, do you think they're high now because of
Yeah.
everything that's going on?
Yeah, because you're already buying it domestically. Like Get FPV is selling it domestically, so they should have already I guess, put the tariff prices.
So all the prices have
Yeah,
gone up because of
basically.
what's going on.
Yeah. Yeah. So if you look, what's the most expensive thing on this list? And it makes sense to me at least. It's the goggles. Yeah. And then usually after that, it would be like the controller. Is that right? Yeah, the controller here. And then it's usually the VTX system. But I'm surprised you said the 03 is only 109. Let's see. Oh, it's broken. But let me see. 04, it's not even in stock. Oh, it is 119.
So the 03, it's an old model.
Yeah.
It's not even posted up there. You have to like search.
Yeah. That's the reality of trying to buy these things. Yeah. I wanted you to experience that for yourself. I don't know if you guys experienced that trying to find some of the parts. You're like, darn it, I can't find it, or it's out of stock, and then you have to go to another supplier. And
I have been trying to find a 16 by 16 flight stack, and they just do not exist anymore. I have a micro drone. 16 by 16. I have a micro drone. Remember that little one that was
Yeah. No.
But that one particular stack, I just can't find.
Yeah.
It's like 16 by 16 is just like a defunct, you know.
Yeah, I don't really hear of it.
Yeah, right.
Yeah.
It was a big thing maybe like 3 or 4 years ago. And
Yeah.
then it just
People still need them.
I mean, they need them, but they're not buying them because they're not out there.
How many people?
Yeah.
Who wants an 04? Why, you can get it?
Everybody's building it, right?
What's that?
Because everybody's building with 04? They
Mm.
wish to build with 04?
What, you mean in this class?
Yeah.
No, we have kits already.
Oh.
If you want to take a box out, you can see it's in the second drawer, the same one that you opened. It has like what does it have on there? If you look at the box, they'll tell you which one it is. But yeah, we're not using the 04 system. What is this? Oh, this is just a homework assignment. I was just having them like research.
How you guys are building it?
No, I mean we are gonna eventually build, which is gonna be, by the way, in like 2 weeks. Oh yeah. Wait. Let's see if we can find the 16 by 16 mounting pattern. 16 by 16. Boom. Right there. Oh, out of stock. See, this is.
Across the board, everywhere.
There's also another.
Because yeah, I could get one of those.
Let's see if we go.
that would fit, but
Let's see if we go straight to Flywoo's.
no, so Flywoo has a 16 by 16 module, but it's like wide. I need like a true
They make 16.5s too. So they make 16.5 by 16.5.
Oh,
So
really interesting.
Yeah, so you have to be careful.
Like I'll bring my little one in.
Sometimes your stack doesn't fit.
Because it's awesome. Like the little.
Oh, this is what you mean by wide. This one right here. What about this one? Oh, sold out. My gosh.
Literally everywhere, and they haven't been in stock. Like I've been looking over the past year and nothing.
Okay. Yeah. This is not. It's already hard enough as is, and now it just makes it a lot more harder. Oops. Sorry. Okay.
What is a flight stack? Like,
Oh.
It's everything.
That's just your flight control board, and usually your ESC as well. They call it a stack because you literally stack things on top of each other. Yeah. You can see in the image that.
Yeah. So the stack that was originally on this drone that I bought had everything built into it. ESC, flight controller, and yeah, it's awesome.
Well.
It's like that big.
If you pull up mine, it links to a stack that's
Pull up yours.
movie drone store.
Oh, there it is.
I thought this guy started. Yeah, almost got close.
Right here.
We have one right now.
That one's in stock,
Look
but
on
it's a 30 by 30.
There it is. Yeah, see, this is a stack because there's two of them. So we have, it says right here, flight stack because it has a flight control, that's a FC. Oh, it has a built-in ELRS receiver, so you don't have to buy that thing separately like you did.
My buddy just helped develop that stack. I'm thinking about switching to it. It's
Hummingbird.
A really good stack.
Yeah.
Yeah, Hummingbird. There's two different ones. That's the like freestyle regular one, and then there's a race spec. The race spec's 20 by 20. The receiver's actually built into that.
Yeah, so that's nice. That's just like one less thing to worry about.
And the receiver in that one is actually diversity, so you can go long range with that too.
We'll take a picture of that. Keep that up.
Which is why I picked that one when I was doing the thing. I'm like, oh, this is this, and this does it. Like when you scroll down, it shows all the specs. And all
So like, let me look at Robert's because his like you don't need to double list it because his flight control board's here, and then if I look at ESC, Well, yeah. Oh, I see. You put it all here. He listed it like 3 things in one. That's kind of nice.
Same with the camera and video transmitter.
Yeah.
DJI.
So, cool. Okay, so yeah. Hopefully that I had this after the other assignment because I wanted you to be familiar with the different components, and then we can actually like look at real life examples. So hopefully this gives you a little bit of a real life picture of what it's like. Okay, this was the quiz on the different components. All right, Matthew, I see you got it right, but I've put an announcement out there because I know there might have been confusion, specifically on the receiver and the transmitter. The receiver and the VTX, those are technically input and output devices, but I already had a dedicated thing for each of them. So hopefully that clarifies. You see, I is the receiver because it's receiving the signal from the radio. F is the VTX because that's sending it to the goggle. Those are still input for the receiver and output for the VTX. But if you look at my list of options by process of elimination, the input here would be a GPS. That would be a sensor. And then the output would be a servo motor payload drop. I've also had, I didn't put GPS as one of these, but yeah, that would, you have to think about it a little bit. Like, yeah. You have your core components. Remember, you always have core components, which is, what's A?
Board.
Flight control board. B?
Is it battery?
Or B?
Is that the motor or the battery?
What letter
Well,
did you say?
B.
B is the
ESC. Yeah, L is the battery. Okay, you see how it's only sending the power signal? The red lines means like it's power, and then the blue means signal. And then C is motors. D, I only drew one, but like a propeller. E is the camera. Why does it go from E to A back to F?
To get the on-screen display.
Exactly.
Transmitting fully to the goggles.
Exactly. So technically you can go from E to F. That would just be like literally a wireless camera. But you wouldn't get the specs from your like flight board, like your speed and the voltage and things like that, which is kind of important.
So you don't die mid-flight.
Exactly. H is the controller, I is the receiver, and then J and K are inputs and outputs, and there's different types of inputs. Just think about your device. Is it giving information, or is it is it like doing an action, I guess, or is it telling you something? I guess that's the thing. So inputs is going to it's going to give you information. Barometer, compass, gyroscope, accelerometer, those are all sensors. Inputs. Outputs is going to be doing some action. So lights, that's an action. Gripper, that's an action. LiDAR, whatever. Oh no, the LiDAR is not an output. That's an input. Another type of output, like a parachute, that would be like it's doing some action. All right, here I know we haven't used it too much, but some of you have already. But again, A is a nut driver. Remember the difference between A and B, if you look closely? Even though they're both hexagon, but just the way iFixit has it color-coded, is just that the blue is a solid. The blue is the like the negative space, per se. The white is the actual like solid driving piece. So A is going to have a pocket that is a hexagon shape, and that's why we call it a nut driver, because you actually put it over the nut and then you can tighten and loosen. And then B is the hex driver, because it's just the hex shaft. Everything else is basically a shaft. You can see only A had the reverse color sequence. Oh, these are repeated. That's why I didn't put letters on it. Okay.
J and 8.
When you
Yeah, you have to scroll in.
way in.
I couldn't, yeah.
Because normally,
Yeah, maybe I should remove that. That's kind of hard to see, isn't it?
like I couldn't zoom in enough.
Oh.
But normally JIS shows up as the larger one in a lot of things.
Yeah,
Like,
here.
As you put the rounded, that became filler.
I can see the rounded. So J should be Phillips, right?
Yeah.
J is Phillips. Yeah.
But it usually shows up as the bigger one on a lot of.
Oh, I
and
see.
Phillips shows up as the smaller.
Yeah. That one's.
So I got it wrong initially, and then went back and I was like,
Oh,
I know
okay.
what I got wrong.
Okay. Yeah, that's right. You get like 2 attempts. Yeah.
I do that too.
Okay. Cool. I think that's it for the homework and quizzes so far, right? Because we didn't actually. I didn't set the right date for the one that was supposed to be for last week, but yeah, watch the video if you forgot about the McMaster thing. That's what that quiz is about. Plus soldering equipment, which hopefully by this point you are familiar with.
Tell them where the McMaster is up there, where the link is. When you go to
Oh, okay.
your recording lectures.
Oh, okay, yeah. So in case you're not aware, all of these recordings I put under course information start here, lecture slides and notes, and then here's a YouTube playlist. So if you want to find that particular video, it's going to be right here. Okay, I just need the part number. Here it is. Toward the end of that video, remember? Because we talked about it. Here is also, here's where I put my recommended stuff. And then I also made a Google Doc per, there's a suggestion. Like, I put some suppliers on here. It's open for editing, so feel free to throw your suggestions on there too. So some of these are like manufacturers, so they're only going to sell their own component. So like Beta FPV, for example, that Matthew bought the stuff from, they sell Beta FPV only components. But then you can buy it from resellers like Get FPV, that's a reseller, Race Day Quads, Pyro Drone, Newbie Drones. Newbie Drone's kind of both. Newbie Drone has its own like private label, but it also resells other things. So just keep that in mind if you like go to certain stores. It's only their own thing. Mm-hmm.
Do any of these companies go and like promote their stuff like locally, like the ones in Florida or LA? Do they actually put events like locally? Or like trade show stuff? If anything, maybe none of that.
I haven't really seen any. Yeah.
Pop-up events, how do you go?
Yeah, I know they sponsor stuff, but I haven't seen them actually like, because they're like kind of more of an online presence. Yeah. Oh, you dropped some pennies there.
DigiKey.com is one of them.
DigiKey is for getting legit, like, you want to buy the chip that's broken. That's what DigiKey is for. Not so much like FPV, like pre-made like boards.
I was writing the ones down in the car, in the class, and blackmarketfpv.com.
Sounds legit. Why would they call it that? Okay, let me see here.
I've used them a few times.
Oh, you have? Okay, so you can vouch for it? Okay, all right. I've never heard of it.
Ship out of New York.
I started writing a bunch down when people start saying
So it's domestic?
I used them because Fiber Drone was sold out of the Mobula 6.
You say it's New York?
For a good price, yeah.
Okay, alrighty. I put that on.
RC hackers.
Are you doing sites right now?
Yeah, what else you got?
533.com.
This is also editable, by the way. You guys can, if you go to 533.com.
No, the batteries was RC hackers.
So what's the website?
Oh, 53. Okay, so the one I just said was 533.
533.com?
Yeah.
Okay. Didn't show up on my Google search.
No, well, it's the word 5 and then 33.
Oh, F5.
These
Of
kids.
course. The word 5 and 3.
Yeah, you take a basic marketing 101. That's a little bit, yeah, it's a little bit hard for people to know if they mean one thing or another. Okay, where are they based out of? Do you know?
They're like based out of like Tennessee or something, somewhere Midwest.
Okay.
Somewhere Midwesty.
All right, I'll just put that on here. Yeah, cool. Yeah, feel free to contribute. Notice I did not put Amazon on here. It's technically an okay, you can buy stuff on Amazon, but they don't have the level of I guess, filters that you would find on a dedicated FPV site. So if you're gonna buy on Amazon, you better know what you want to get. Don't go there to browse. Go there to find a specific item. Yeah, because there's just if you look up like ESC, you can't filter by like current and like other sizes and stuff. It's just gonna be like a big open list. So yeah, but yeah, if you could do is you can like try to find things on the other website, and if they're out of stock, then copy and paste that like specific item into Amazon and try to find it. Yeah, you could try to do that. Be aware though, a lot of sellers on Amazon also don't know what they're doing, so they may have mislabeled things too. So just do your homework. I say that with a word of caution. Okay, and then other things in here that might be useful is like previous slides and YouTube videos if you want to look ahead to what we might expect to see. Yeah, that's basically it. So remember there's the quiz that was supposed to be due. That one's on McMaster and soldering equipment. And then there's the one that's due at the same time. So 2 quizzes. That one's going to be on electricity. So what we talked about today. Let me see what we're going to do next week in case you want to know. Hardware. Okay. Lipos. Okay, I think we might start talking about lipos. And then after that we can start building things. Yeah, and then after that we can start building things. Okay. All right. So we can we'll talk about lipos, and then we can still do more soldering if you want. That's kind of going to be what the format is going to be like going forward now. It's going to be like I lecture in the beginning, then we do some hands-on thing. Like since people are buying their own kits, we also have kits, so if you don't want to buy, it's fine. I'm going to be showing like how to build the specific kit we have in class, but people are going to be working on your own thing, and that's fine. Yeah. Okay. If you want to buy a kit, you have basically until October 7th. That's when we're actually going to start building things. So 2 weeks from now. Yeah. Any questions? Yes.
The kit that was recommended.
Yes.
I ended up buying myself from KPV.
Yes.
It doesn't include instructions. Where would I find good instructions for that?
Here. I'm your instructions. So.
There's no video tutorial. That's another thing. Almost everything you're gonna buy is not gonna come with instructions.
You can maybe go on YouTube. I've tried to search myself. I ended up doing a little bit of like just self-exploration and YouTube video, but the one YouTube video I saw out there was not very like, it was like kind of far away and I just couldn't really see it much.
If you're lucky, they only give you like a QR code PDF. And
there is no PDF on this one, I'll tell you that, yeah.
I'm said if you're lucky.
Oh yeah, this one for sure has nothing. But that's fine, I'm here to help.
No, I'm grateful. But how do they expect you to put it together?
Yeah, basically.
Buy more parts.
Yeah.
Multimeter.
Exactly.
Sounds like somebody should make movies.
Yeah.
Videos and
Yes. I mean, this could be a good time if someone's a YouTuber. Film your build process. Be that video. Yeah, we could use more of that because honestly, I feel like the FPV community is like kind of still like people maybe. I think it's probably getting a little better, but it still seems kind of like people do their own thing, a little gatekeeping a little bit. So, yeah. So.
Once there's a consumer FPV drone out there that's just plug and play, I think it'll take.
There is. It's the Vada.
Well, I mean, yeah, but like the DJI, stuff, not everyone, like with all the regulations that are coming with DJI, people are going to stay clear from that.
Yeah.
Plus, DJI Avata is not like an
Right, I know. What we need is something that's like buildable, but with great support.
Exactly.
Yeah.
Once they start marketing it to like the younger kids that are going to be into that stuff.
Right.
You should be the college that supports it.
Yeah.
One model.
Yeah.
Everyone was flooded with